All right, good afternoon, and welcome to another webinar in our Power Gen ENTRUST Solutions Group webinar series. Today, I'll be talking about steam turbine startups, specifically some of the different key factors that govern startup practices. Also, some of the failure modes you have to be careful for, and then we'll talk about how you can optimize startups with your existing plant equipment. So can be quite economical and provide significant benefits to plants to make startups quicker, but also have them consume less life per startup. So today I'll be presenting Tom Reid, Director of Engineering for ENTRUST Solutions Group. We're previously TG Advisors Incorporated. I think many folks know us as that. We still exist, but we are part of the ENTRUST Solutions Group now. All right, before we get into the material, just a little bit about ENTRUST Solutions Group, and then a little bit more about TG Advisors. So ENTRUST Solutions Group, formerly known as EN Engineering, has been around for 20 years. And it's a consulting firm that's across oil and gas, pipeline, power generation, and also across distribution and transmission. So roughly, I believe, 3,500 people now, and quite a large business. So work all across of North America, providing technical support services for really anything that folks need. So on the power generation side, we've got TG Advisors, who is turbine generator advisors, so anything rotating equipment, but also any type of boiler issues, balance of plant, you name it. We've got Kestrel Power Engineers, who focuses on excitation systems and NERC compliance. And then we also have EN Automation that focuses on controls and automation. So just quickly on TG Advisors services highlights for those that aren't familiar with us. Really, we're a third party that specializes in rotating equipment. A number of us have come from the original equipment manufacturers, such as General Electric, Siemens, Westinghouse, you name it. And we have quite a bit of folks that have also come from the utility and operations side. So today's topic is certainly operations. So we have quite a bit of experience with this equipment and evaluating this equipment and evaluating failures, but we don't sell parts. We just sell technical consulting services. So we really do provide an independent opinion to owners and operators. So you name it, we do it on the consulting side. So health assessments of equipment. Today we'll talk about optimization, flexible operations optimizations, owner's rep, field services, shop surveillance, failure analysis, pretty much any type of service that would be required. All right, so now we're actually going to move into the startup optimization discussion. And really, I like to start with why optimize. First thing is we've had an influx of renewables over the last decade or more that has caused for varying power demand and varying power prices throughout the day. So we got wind turbines, we got solar, we've got all types of other types of renewable sources that can be intermittent. So traditional generation sometimes has to respond to that demand. Gas prices, natural gas prices have been fairly low over time here recently. So it is economical to run these combined cycle plants in many cases. But we do sometimes have oversaturated supply versus demand. So there's benefits to being able to cycle either down and load of these assets or to actually cycle them on and off. So we don't see a ton of baseload assets. I mean, you still see the nuclear steam turbines that pretty much come up the rated power and stay there, although there is some discussion on load cycling there as well. But we do have quite a bit of variety of age of assets out in the market. And what you have is some of these older steam turbines that are competing either from they've just been around, 50s, 60s, 70s, 80s, even with these newer combined cycle units. You also have some units that have been repowered from conventional boilers to combined cycle arrangements. So some of the steam turbines still operating are from the 50s or 60s, and they're being forced to compete in competitive markets with plants that were more designed for cycling and are much newer. So we got to somehow be competitive, but also make sure that the equipment is safe. So reduced start times and lower minimum loads provide economic benefits, which is reduced fuel and water costs, and in a competitive dispatch market, potential for additional run opportunities. And the other reason to optimize is sometimes we have concerning conditions with our units. Could be something like flaws in a rotor. And we want to make sure that we manage that as safely as possible, such that, the rotor doesn't have any significant condition concerns. All right, so we'll start with technical considerations. Really, the purpose of this section of the webinar is that when you go back and look at your steam turbine startup process, you'll start to understand a lot of the why behind some of the requirements that you adhere to through that process. So let's start with what failure modes are we concerned with? When we're cycling on-off cycling, we're going from basically no speed up to rated speed, which often is in the US 3,600 RPM. Nuclear could be 1,800 RPM, or could be any speed if you have a geared drive. But the point is, you're going from basically standstill up to a speed, and then eventually you're coming back down to standstill. So anything that rotates, that's a significant stress cycle. And you can only do so many of those stress cycles before a crack would initiate. The second thing that's happening is we're going from cold temperatures or from lower temperatures to a very high temperature. So we also have thermal stresses for all parts, whether they're rotating or stationary components. So doing this a number of times eventually leads to what we call low cycle fatigue cracking, or essentially cracks forming in rotors, blades, casings, generator components, you name it. They're all exposed to stresses. We can also see stuff like solid particle erosion. Essentially, that's particles that are kicked up from the boiler, the Hersig, when you're cycling, and they're sent through the inlet of the steam turbine, causing some solid particle impact damage that wears away surfaces over time. We can see issues during startups with vibration. We're going to pass through critical speeds of the shaft where we see increased deflection. We also have something called differential expansion, where the rotor and the casing, they're heating up at different rates. And there's potential, if we don't have sufficient clearances in the unit, that stuff can touch that's not supposed to, leading to damage or more vibration. We can also see casing distortion. Some of the secondary failure mechanisms, high cycle fatigue, that's vibration-based cracking. We'll hit on that a little bit later. Water droplet erosion. Typically when we're starting up a steam turbine, the conditions of the steam are not great. So we can get quite a bit of moisture and also a little bit of erosion damage from that. On the operations side, we got to be concerned about vibration. Water induction, that's when we accidentally throw water into an operating steam turbine, can cause quite a bit of distortion. Historically, those have traditionally happened during startup shutdowns and load changes. I mentioned differential expansion already. We could have boiler or heat recovery steam generator upsets. The risk of overspeed is always accelerated, and same with loss of lube oil. So those are kind of operational events that could occur, but for various reasons, they tend to happen more during these transient operating events like startup shutdowns and load changes. What I'm showing on the right side of the screen is just some examples of cracks that have developed in units. Both of these are casing cracks that have developed from cyclic operation. So quite a bit of on-off cycles. You can see these are stress concentrations from the threads in this bolt hole or from this corner. And wherever we've got a stress concentration, these cracks initiate following these repeated stress cycles. All right. I alluded to earlier that we do have quite a bit of differences or quite a variety of steam turbines still out there operating. I'm going to put them today into two categories. The first one being vintage. So we got to be very careful with these vintage units that are still operating because they're nearing their design life. For the high pressure, high temperature rotors, that may mean that we have creep or embrittlement concerns, solid particle erosion. We may have a rotor bow that's developed, and we may have casing cracking. For the low pressure turbine, typically what we're worried about is stress corrosion cracking or water droplet erosion. So these are failure modes that are likely present, and we're having to manage in that vintage unit. They're also typically less modern designs. Most of the rotors have a bore down the center. Essentially, after the forging process, you would come back and bore out or machine out the center line of the rotor to remove impurities. However, having a hole in the center of your rotor increases the stresses. So we got to be very careful with those bored rotors. And you've probably heard of boresonic inspections in the past, which we do at routine basis to look for flaws on that bore surface or subsurface and to track the growth over time to make sure that we don't have any flaws of concern. More traditional rotors, improvement in forging processes is such that we don't typically require a bore anymore, which ultimately allows you to be a little bit more aggressive with your startup process. On the less modern designs, oftentimes the spend is limited because you're trying to get them through to retirement. You may have gone a long time without a major outage, etc. So you then move over to the modern or retrofit rotors, and you'd like to think that they're pretty much trouble-free since they're earlier in their life cycle. Less accumulated stop-starts, less operating hours, unlikely to have a bore. But I think some of the challenges that we've seen is the design conditions have been pushed. So a lot of this vintage fleet was more that base loaded, come turn on, stay at power, and then shut down a few months later or for an outage. Now we're cycling full combined cycle plants once or twice a day in some cases, chasing renewables. We've also seen an increase in the inlet steam condition temperatures. So 1,050 degrees Fahrenheit or in that ballpark is very common these days. It used to be up to about 1,000 degrees in the past. And they're designed for enhanced performance, could have some tighter clearances, could have some advanced sealing designs, but in some cases that provides operability challenges. All right, so one of the most, I'd say, fundamental things to understand about steam turbine startups and why we do things the way we do is going to be covered on this slide. So I'm actually going to start in the top right corner with these images and explain a concept here. And what that is brittle versus ductile fracture. So what we have here on the left is a brittle fracture of steel. You can see very cold temperature, 80 K, which is minus 315 Fahrenheit. Our rotor will never get that cold in a steam turbine, but for illustration's sake, what you can see is a very small flaw caused this ultimate failure of the steel bar. So that's known as a brittle fracture, where it doesn't take a large flaw to have this crack reach a critical size and fail. because we have very poor ductility and very, very poor material properties when this material is cold. To the contrary, here we have a ductile failure, which is 300 K now, which is approximately room temperature. What you can see is the crack could grow to a much more significant depth or size before we ultimately had this failure. So we call this a ductile failure. And when we are looking at rotors, we want them to exhibit ductile behavior because there's going to be flaws, there's going to be impurities in the rotor, and we want to make sure that it's not going to fail. So we want to allow for as large a crack as possible prior to failure. So explaining that concept, what's really important to know is that high temperature rotors, so your high pressure and intermediate pressure rotors, are made from different materials than your low pressure turbine and your generator rotors. And those high temperature rotors require temperature to act ductile. So when we start, when we're in a cold state, the rotor is going to act like this. Maybe not to that degree, but it's going to require a much smaller flaw to potentially have a rotor burst. As that rotor heats up and it gains more temperature, it has an improvement in material properties, also known as fracture toughness, and it now allows for much larger flaws before we could have a burst event. So what we're trying to do and why we require holds on many cold starts is we want to keep that rotor at a low stress state. So typically that means holding at a speed below rated speed for a period of time to gain temperature such that the material properties improve, such that, you know, I'm not at risk for this burst condition. So if your startup is calling for these holds and you're not adhering to them, there's more risk for a rotor burst event, which obviously is not something that happens very frequently, but it's a very significant event. So it's something that we're obviously very careful to avoid. So that's one comment, is that we gotta get heat. So that's what we're showing in this plot. Essentially, you start out, this is fracture toughness. We want this number to be higher when we're cold, typically up until like 200, 300 degrees Fahrenheit. We're going to be down on this brittle type behavior. And then when we get up higher, we get improved ductility and we can withstand much larger stresses. Okay. The only other complicating point is, like, with time, these rotors actually embrittle and they require more temperature as they get older and have seen more service history to get those good material properties that they could achieve at a lower temperature earlier in life. Okay. So again, low speed holds are there to help gain temperature in the rotor to improve the material properties before we push it to a high stress level. Okay. And to the contrary, when you're doing a warm or hot start, you don't typically have these holds, or you have very short holds on, say, a warm start. And the reason for that is the rotor metal temperatures are already well above the point they need to be to have good material properties. So therefore, I don't need to spend a lot of time at low speeds. I alluded to just a minute ago that a phenomenon called embrittlement occurs, and it happens around an operating temperature of roughly 800 degrees. That's where we see peak embrittlement. And to not get too technical, essentially what it does is it heat treats that rotor over time, and it just requires more temperature or a higher temperature with time to get to the point that we're getting that good ductility again. So what we have on the left side, this was a rotor with high temperature rotor with over 400,000 hours. And you could see that it became so brittle that the serrations or the lugs just peeled right off the rotor from embrittlement. So on a rotor like this, we would have to be very careful to make sure that we heat soaked it longer. We held longer at those lower speeds such that we got good temperature and good ductility again. All right, a couple golf references in here, but hopefully it explains the concept. So I've talked about we often have to hold at speeds less than rated speed. It's very important that we adhere to what's in the instruction book. So we can't arbitrarily pick speeds because we like the speed, or maybe it heats quicker, or the rotor seems to be a little smoother. And the reason for that is on most units, the last stage or the last couple stages of low pressure turbine blades are tuned. And what that means is that we selectively control the mass and the stiffness such that their frequencies, their natural frequencies that they're going to vibrate at, do not correlate to a multiple of running speed. If we have a blade vibration frequency that's equal to a multiple of running speed, the blade is going to fail rather quickly from high cycle fatigue. Okay. Well, the same is true when we back off speed. So what we have on the left side is a Campbell diagram. It's showing the natural frequencies of the blade, first mode, second mode, third mode. And what you're looking at is here's running speed. And we just want to make sure that these natural frequencies, don't hit at 1 times, 2 times, 3 times running speed, 4 times, 5 times, 6 times. So we can tell here it's a well-tuned blade. The lines of the actual frequencies are sitting between multiples of running speed. Well, the same is true for hold speeds. So if I look at this line where I say okay, the green line, I'm still good. I don't have any, if I'm holding at that speed, I don't have any resonance predicted on the blade. But if I were able to, or back up to the red speed and I held there, I would have 3 times running speed would be resonant with my first natural frequency. So the challenge here is that you don't have any instrumentation on your unit stock that would tell you if you have blade vibration. You do have measurements at the bearings, but those are looking at rotor vibration. They're not looking at blade vibration. So you could be holding at a bad speed and causing damage to your blades, but not knowing it. So the best way to protect against this is just to adhere to the hold speeds that are in your instruction manual. And if you were to get a retrofit LP rotor, making sure that you get updates to those hold speeds as needed. Another important thing on steam turbine startups is steam to metal mismatch. Essentially what this is the difference in temperature between the steam and then the different relative to the metal temperatures in the unit. So as you can imagine, the higher the difference, the more thermal stress that occurs, because it's like taking something that is cold and pouring hot water into it. It's a significant stress cycle. Or I guess another way to look at it is like if you've ever taken a glass pan out of the oven that's hot and you were to put cold water on it, it would just shatter, right? So we want to keep the steam to metal mismatch low because we want to keep the thermal stresses low. But at the same time, if we don't have any mismatch, then we don't get any heating. So the higher the mismatch, the quicker it'll heat, but the more stress. So we got to manage these things. If we have a no board rotor, a lot of times this is a combined cycle. It's a no board rotor, so the startup doesn't call for any hold speeds, but they do have steam to metal mismatches approaching 600 degrees Fahrenheit, which ultimately is going to lead to cracking, which you see on the left-hand side. Where the cracks show up is where we have stress concentrations in the unit. Anytime we have a geometry change is a stress concentration. you take the nominal stress and you multiply it by a factor to get the stress in that location. So the sharper the notch, the higher the stress concentration, the smoother the radius, or the larger the radius, the less of the amplification of the stress. Okay? But end of the day, we can only cycle so many times until we get cracks on high stress components. All right. We also have to be worried about clearances. So when you're going through an outage, sometimes there's a desire to make clearances very tight again, particularly radial clearances, to try and get as much performance as possible to limit the leakage in areas that don't contribute to power production. However, that can present significant challenges with cycling. We want to be able to be flexible, start the unit quick, and if we put these tight clearances in coming out of an outage, we may not be able to start the unit because we're getting such significant rubbing, or we may eventually just rub out the seals or damage the seals and be right back to where we were previously. So you certainly want to consider your approach in setting seal clearances in a unit that cycles. So radial clearances, every time we go from like turning gear speed or no speed essentially up to rated speed, we're going to pass through one or more critical speeds of the shaft, where that shaft is going to deflect more. This is what that first motor vibration looks like, but we get the most deflection in the center of the rotor. So we got to be careful. The likelihood of rubs during that time is more. So that's one thing. Axial clearance. We're going to have differential expansion because everything's going to heat up differently. Rotor casing, rotor length is also impacted by heat, but it's also impacted by speed. So a lot of stuff going on. We don't want things to touch that aren't supposed to. Metal on metal can create quite a bit of damage. So making sure we have sufficient clearances is important for cycling. So here's another golf reference, but as you can see here, taking the shot without enough clearance, and we end up with a broken golf club. So not too much different than what we've got in some of these cases. All right, so now moving a little bit more into startup parameters, and it's quite a bit going on. And when I talked about earlier, why there's a lot of issues, or why issues typically occur during this time, is that there is so much going on and everything's changing. A lot of steam turbine startups are still manual or semi-manual. Some cases they're automated. Gas turbine startups tend to be more of a push button. So what are some of the stuff we're looking at just to be able to roll the turbine? We're looking at superheat requirements. So we want to make sure that the steam is superheated enough such that we don't get wet steam in areas that we don't want it. We need to make sure that our steam lines, piping leading up to the turbine is warmed up. We're going to look at rotor eccentricity to make sure that the shaft has all the temporary wobble out of it, such that we don't get too high of vibrations when we run it up. We're going to look at lube oil temperatures as well, to make sure that the oil is warm enough such that we get good vibration dampening from the bearings and the oil film. We're also going to look at LP condenser vacuum levels to make sure that we have appropriate vacuum levels to bring the unit up. We have to be very careful with vacuum levels throughout startup to prevent potential blade vibration issues in the LP, low pressure turbine. So we do all that stuff, and then we get the turbine roll and soak. So we got to look at the OEM acceptable hold speeds. I just talked about that. We can't arbitrarily select them. We got to look at steam to metal mismatch. The higher the number, quicker we're going to heat, but it's going to create quite a bit of stress. Lube oil temperatures, we got to continue to look at them throughout the process. We got to look at shaft vibration levels. We got to make sure we're adhering to the correct heat soak speeds and times. We got to look at differential expansion. Oh, and by the way, there's steam chemistry as well. So a lot going on and a lot of opportunity for issues. Let me just mention one other item before we move on. We typically split the startup when we're evaluating it into 3 sections. Typically it's pre-roll, which a lot of times that includes a pre-warming process depending on the turbine manufacturer. That's phase one. Phase two is the roll to speed. So that goes from rolling off gear up until we put some load on the machine. Phase two. And then the third phase is loading of the machine, going from closing the breaker up to eventually the dispatch megawatts. All right, so I think most of you joined this webinar to understand what you can do differently. So couple things I want to highlight here, or some of the opportunities. I look at this where we have a lot of different knobs and buttons, and depending on the unit, we do different things, right? So the first thing is we can change steam conditions potentially, temperatures and pressures. So we can reduce the roll temperature, which has a benefit for thermal stresses. We're going to have lower steam to metal mismatch, but we do need to make sure that the steam is still hot enough to provide rotor heating. We can look at putting steam into the unit quicker, which is going to shorten our startup process and getting us rolling faster. We just need to make sure that, again, we have good superheat such that we're not putting moisture into the unit where it's not designed to have moisture. If you've got a steam seal system or an auxiliary source of steam, you can use that to preheat the rotor. I'll show you some examples, both analytical and in practice, of the benefit of that. So we found, if you're in a day ahead market, you're going to be called and you have the ability to put those steam seals on, go ahead and do it. It gives you some free heating and allows you to make the startup a little bit quicker and safer. We've worked with some folks that have actually put in aux spoilers as an upgrade if they don't have it, just to be able to cut some more time off the startup. And then you get into phase two, which is you've rolled the unit. You can look at optimizing the times and speeds. So as we talked about, we like to be very careful, particularly on vintage rotors, when the rotor's cold. And I'll show you some examples here shortly. So sometimes we put in a low speed hold, assuming it's allowable, such that we can get some of that heat soaking and we can let that steam to metal mismatch dissipate and that thermal stress come down before we increase to a higher rotational speed, which increases rotational stresses. And then, with high speed holds, the higher the speed, the better heat transfer, the quicker heating we get as well. And then eventually we get up to full speed. So we're at peak rotational stresses and we put load on the unit. And some startup processes, there's quite a bit of variation across the industry, but some OEMs actually call for you to slow down the process at that point. And typically we're not a big proponent of that because there is some challenges of sitting at low loads for very long periods of time. We have to worry about LP blade vibration. We have to look at back pressure levels very closely. And we don't get a ton of additional heating because you're not getting a lot of flow at that low load point. So when you look at temperature trends, you tend to kind of level out over time. So I think you have to look at all these things and you can make some good judgments on where there's opportunity to make modifications. So I mentioned the steam seals. Here's a intermediate pressure rotor, and what's interesting is here's the inlet, right? And then here's the exhaust and the gland or the steam seal area. So what's interesting is that the slowest part and the limiting part of the rotor to heat up is going to be this back end typically, because the steam is coming through the inlet and it drops temperature, drops pressure by the time you get back here. This is also the thickest part of the rotor. So it's going to heat the slowest. Well, if I can put those steam seals on in advance, it's essentially putting some heat to the back end of the rotor. And that's going to start to conduct through and give you some heating benefit from the back end first, which is the part that heats the slowest when I actually start rolling up the unit. So it's a good way to cheat and get some free heating in advance of actually rolling. So what we're showing over here is just some modeling, and the biggest benefit is at stage 7, the back end. Limited benefit kind of up front, but that's okay because that's going to heat the quickest once we actually emit steam to the unit. So if you're on a day ahead market, you have an aux source of steam, go ahead and put them steam seals on. Typically 350 to 400 degrees Fahrenheit is kind of the temperature range that we see, but we've seen lower, we've seen higher. Here's an actual unit where we did that modeling, and we had the benefit of looking at an IP blade ring temperature and a first stage metal temperature. So again, these would see lower temperatures because the steam seals are on the back ends. But we saw very good correlation between what our model predicted for heating that we would see propagate through the rotor and what we actually saw in the casing thermocouples, 175 and 150. So again, it's kind of free if you're able to do that. So when we start to look at the startup, now we're getting more into the actual evaluation part. These are the things you want to look at and understand. First thing is operating hours and starts. What have we accumulated? It tells us how many failure modes we're probably dealing with at this point and how far they may have progressed. Are we close to the end of life or we have a lot of life left? We'll look at historical outage reports, specifically the non-destructive evaluations. You have a bore, you want to understand the bore condition. Ultimately, what you do is something called fracture mechanics calculations, but it's looking at the flaws that exist and looking at what a critical flaw size would be, and then you can calculate kind of how many times you can cycle it to grow that existing flaw to a size of concern. If you don't have bore, you may have a peripheral UT where they look from the outer surfaces inwards, again, to look for flaws in the internal to the rotor. We can actually develop a good finite element analysis model, which allows us to, with your operational data, it allows us to calculate rotor temperatures throughout all of startup, and it allows you to calculate rotor stresses throughout startup as well. From those things, we can, and knowledge of material properties, behavior, we can calculate critical crack sizes throughout startup. So it allows us to understand how conservative or anti-conservative a startup is, and it allows you to set a baseline so that when you modify things, you can quantify the improvement. One thing to keep in mind, though, is that you got to understand the life, where you're at in the life of a rotor. You can't just treat a brand new rotor, or excuse me, a very old rotor as a new rotor. You need to make age-appropriate assumptions, particularly around material properties and embrittlement. So ultimately, you go through this process, you do your modeling, and then you can recommend startup improvements. To one, you want to reduce life consumption per start. So that allows you to extend the life, but you also want to save time, right? So it's kind of a win-win, which sounds counterintuitive, but with kind of these advanced tools and analysis, it absolutely can be done. So just quickly, what I said verbally, we call it PI data, but it's because that's what most folks use, but operational data is exported from a real turbine startup from your unit, make a finite element analysis model of the rotor, and we could simulate the startup on the computer. We can simulate changes, and what we're looking at is stresses throughout startup, particularly on that center line or bore surface, and we're looking at temperature throughout startup. With temperature, we can figure out material properties throughout startup. So remember, one of the first things I said is that the material properties for the high temperature rotors change throughout the startup. It starts brittle and it transitions the ductile behavior. So we got to incorporate that knowledge as well. So here's an example of a HPIP retrofit optimization. Really, the takeaway on this one is going to be the pre-warm period. So depending on the OEM and depending on the vintage, you may have a process called pre-warm by pressurization or a pre-warming. And what this does is kind of pulses in steam. We can't just emit significant steam into the casing because then the turbine's going to roll off gear. So we just pull steam in and get this slow, gradual heating over time. The problem is if you follow this process to the T, you end up with a very often slow process. So in this case, they had to get to 350 degrees first stage HP metal temperature, and it took roughly 10 hours of this steam pulsing to get there. So when you look at it, it's like, all right, if I cut off this final 4 hours, the difference is only 50 degrees of benefit. So you kind of get diminishing returns with time. If we were to roll up to a low speed hold, we would get better heat transfer, a little better flow, and a little bit quicker heating. So there's ways to modify that and cut back on the time without compromising the safety of the unit. The other thing that was interesting here is they had done a retrofit of the turbine, or the high pressure turbine, high temperature rotors, excuse me, and they had not changed any of the startup practices. So they, as a result, were being very conservative. So 10-hour pre-warm, then they go to speed very quickly, and then loading was about 18 hours, but some of that was dispatch driven, some of the low load holds. But you can see that they were following the instructions of, low load hold and trying to get temperatures up that way. Now, the problem or the point to think about is, like, by the time you reach full speed and you have load on the unit, if you were going to have a failure, it would have already occurred earlier in the startup process when the rotor was cold and brittle and had that high steam to metal mismatch. So we typically don't see a lot of benefit in this extended hold once you get to low loads. So just something to think about. Just because, again, the material properties are so much better at that point. So the rotor can withstand larger stresses, and it's in a good state. So just wanted to show you some of the improvement. In this case, we were able to cut down the pre-warm process by 6 hours, and we only lost about 60 degrees in metal temperature. In some units, we would have accounted for that by adding the low speed hold, but in this case, it was a retrofit boreless rotor, so the stresses were significantly lower than the original design. So we kind of left the balance unchanged. And then for the loading process, we took 4 hours to get to rated load. We cut back on that low speed hold quite a bit. So really getting to 500 megawatts in 10 hours, where previously it was 30 hours. But again, some of it was driven by dispatch requirements. So even if you look at it 20 hours versus 10 hours, it's still a significant savings. And, we haven't compromised the unit in any manner. All right, let's talk a little bit on a vintage optimization. I think this is wrapping us up here as our last case study. Just some pictures I grabbed from the web. This is more of a vintage unit here, high temperature, and then low temperature, transitioning into low temperature. Here we're showing some borosonic equipment and some visual indications on a rotor bore. Again, that's the surface that was cut out on the center line of the rotor following the forging process. Sometimes you'll even see a bottle bore if you look at your bore diameters, because there might have been a flaw that, like you see in these pictures, and then they would have come in and machined that out, and it ends up increasing the diameter of the bore in a section, which we call a bottle bore. So I know these plots have a lot going on, so let's take a minute and explain them. So these are coming out of our rotor models for optimization. So what we're looking at here is stresses at the bore. So if you look up here in this top corner, It's the stress at the bore below each blade stage. So stage 9 is basically right here, 10, 11, 12, 13. So using this finite element analysis and the steam conditions, steam temperatures, pressures, and speed ramp rates, I can simulate the startup. And what you see is with this startup, if you follow the speed, it comes up to 3,000 RPM. It wobulates. For those that know the various startups, you probably know which OEM this is. But then it goes up from 3,000 RPM right up to 3,600 RPM and starts making power. Low load hold, and then picks up load eventually. So my question is why are stresses peaking so early on? And then you notice they're coming down, even holding at relatively constant speed. The answer to this is that we have two things happening at once. One is we're increasing to a significant speed, 3,000 RPM. So we have quite a bit of rotational stresses, but we also have our peak thermal stresses because we've got that really high thermal mismatch at that point in time. Because again, you may have 400 or 500 degrees hotter steam than you have metal at that point. So when you look at the criticality of the startup, we have to be very concerned about the ability of the rotor to withstand this part of the startup, particularly if it's an older rotor, because it's going to have those poor material properties because it hasn't gotten significant heating yet. Out here, although when we start loading, we see a higher stress peak again. We're not concerned, or not nearly as concerned, because now the rotor has a lot of temperature and it's got very good material properties. So ultimately, like what we get to with all this modeling is a critical crack size. And essentially it tells us how big a flaw can I withstand before I'm concerned about a potential rotor burst. Now, there is a fair amount of like conservative assumptions that go into this, so you probably don't want to look at the absolute value and get too hung up on that, but you can look at the relative difference pre and post optimization. So what we're seeing, because we get those high stresses at that point and we have still poor material properties, so brittle behavior, we get a very big dip in the critical crack size. So that's my point of the startup that I'm most susceptible to failure. And this is saying like 0.2 inch crack depth. Although I had that stress peak again around 5 hours, I have much larger critical crack sizes at that point. So I'm not at risk for failure at that point, which is why we don't like to spend a lot of time at that low speed hold, because if I was going to have an issue, it would have happened here. All right, so you learned a lot during this webinar, and the question is, what can I do to improve things, right? I know it's not easy to answer, so I'll go ahead and give you the answer. I can add a low speed hold, right? So what that does is it allows me to sit for a period of time at a lower rotational stress, because stress is a function of speed squared. So now I'm sitting at 1,000 instead of 3,000. So during that sitting at that low speed hold, two things are going to happen. First thing is my steam to metal mismatch is going to come down. So that's going to lower my thermal stress. And then the second thing is that my rotor temperatures are going to improve, which is going to improve my rotor ductility or material properties. So adding this half-hour hold at 1,000 RPM took my limiting critical from 0.2 inches up to about a half an inch. So significant improvement with that little bit of tweak, and something that, your startups, particularly for older units, come with one startup. Probably looks pretty similar for like a 1950s unit up to like the newer combined cycles without bores. So probably very similar from the 50s to the 90s. And it's very rare that any type of change in startup process would be published with time. So what that means is you're still probably following the same guidelines that folks followed in the 50s, and that you followed from a new unit. So the science has improved, the understanding of fracture mechanics. That didn't even come out to like the 80s. So that wasn't around when a lot of these startup processes were developed. And the understanding of how rotors age as well has improved with time. So I think this is a great example of how adding a small hold and slowing down the startup in that one phase can significantly improve the margin on starting an older unit. Now, we certainly could make up for this time elsewhere, right? Like reducing the pre-warm or reducing that back end, the loading time when we've got good ductility, better material properties. So giving a little bit in this phase 2, run up the speed, I can get it back elsewhere and end up with a safer startup, but also end up with a faster startup still. So the low speed hold allows for high thermal stresses to dissipate or reduce at lower rotational stress levels. It also allows for some improvement in material properties. All right, so we're at the last slide. I'll go through this, but we welcome any questions. There is a chat Q&A. Feel free to start putting those in there if you have any. If you don't, that's fine. My contact information is right below here, so feel free to follow up with an email. And I think this will be posted on YouTube at some point as well if you want to get a refresher and pass it along to a colleague. All right, so closing comments. Significant fuel savings and dispatch benefit for steam turbines that can start quicker and operate also at lower loads. We didn't talk about minimum load optimization today based on the timing we had, but we've done quite a bit of that work as well, and happy to have an offline discussion with anyone there. There are opportunities that exist to safely reduce cold start times without capital upgrades. I showed you today. You can do modeling, or you can even just look at some of your operational data and make some judgments, look at your inspection reports on where timing can be saved. The approach that we talked about utilizes recent inspection results, finite element analysis, and modern fracture mechanics principles. And in our experience, cold start times on older steam turbines can commonly be reduced by 25 to 50%. While still adhering to critical OEM design parameters and requirements. So I think that's the key thing. We're still operating within the bounds or the key bounds of what's necessary with hold speeds, things like that. But we're able to get units online much quicker, but still safely. So with that, that's all I have. Thank you for participating today.